So our first speaker for today is Yikun Wang from Caltech. Please take it away.
Yeah. All right. Thank you again for the opportunity here to speak about this interesting topic. Before moving on, I'd like to thank my collaborators here, Mr. Latrina from Firm Lab in Chicago, Claudius Krause, now at Rutgers, transferring to Harvard, and then Janelle is from University of Minnesota. So, to tell you a story about synchronous resources, I'd like to start from zero temperature, this very simple picture. So at zero temperature, the electrical symmetry is broken, and that is pretty much determined by the mass term here. Your favorite Higgs potential. So we know from measurement that this Higgs mass here is negative. This term here is negative. That drives this shape of the potential, and that's your symmetry breaking. Moving on to finite temperature, turns out the leading order thermal correction to your Higgs potential is actually this thermal correction to your mass term here. And the term this depends on the size and also the sign of this thermal correction. The Higgs potential can display different behaviors at finite temperatures. Of course, this thermal correction is determined by your underlying empirical constant that talks to the Standard Model Higgs. For example, a scalar degree of freedom running in a loop is going to give you a correction linearly on your coupling constant. And both fermions and the bosons are going to give you distributions like square, proportional to square of your coupling constant. And this is going to be crucial next for the synchronous restoration. Of course, in the standard model, you know pretty much everything that talks to the Higgs. That means you can calculate this thermal correction from first principle. And it turns out this thermal correction to the mass term is positive. So that tells you at a temperature mass of much higher above the electric scale, you're going to have a symmetry restoration. So this electric symmetry is unbroken or preserved at very high temperatures. So what's actually interesting before is what happens in between here. Basically, when and how the symmetry, electric symmetry was restored, or from the other side is broken. And this process is what we call electron explanation. And this is a particularly interesting phenomenon because there are so much possibilities can be associated with electron explanation. For example, it is considered to be a very good venue for electroweak baryogenesis to explain the matter-antimatter symmetry mystery because it can provide 2 out of these 3 subcloud conditions for baryon symmetry to be created. So this is what we call electroweak baryogenesis. And also, if the phase transition here, as I described by this yellow line here, is strongly first order, it can also generate stochastic reaction wave that we heard a lot the last couple of days. But I need to tell you a bad news first about standard model based on mapping simulation because we know the particle contents, we know everything about the behavior of finite temperature Higgs potential. That the transition here is rather smooth crossover. So basically that disables the possibility of both electroweak baryogenesis and a stochastic wave background. So that is kind of boring. That's why people have been thinking about going beyond the standard model. If I attach my Higgs sector with some BSM for freedom, can I change the behavior here, how the electrical symmetry was broken? And now let me change to a slightly different diagram with more information where the axis is Higgs vacuum expectation value as a function of temperature. You can see clearly the standard model picks up a non-zero vacuum expectation value very smoothly. And a lot of research and effort has been devoted to study the behavior here at the electric scale around 100 GeV each, where with new physics degree of freedom, you can actually modify the behavior here so the Higgs can pick up the non-zero vacuum expectation value abstractly or discretely. And this is a feature for strong first order electroweak phase translation. And here we can talk about asymmetry creation, we can talk about stochastic wave background. But today I want to go beyond this picture and talk about the static difference possibility. So I don't want to restore my electroweak symmetry at the electroweak scale. Instead, I want to let a non-zero vacuum expectation value persist up to very high scale. Let me be agnostic, I call it the UV scale. There will have mutable freedom or even UV completion of your model that could change the behavior of your electroweak symmetry. But before that, from this UV scale, you can talk about hundreds of TeV or even many others, so many above that. from there down to the electric scale and even zero temperature, I have my electroweak always broken. So this is what I call electric symmetry non-restoration. And this is interesting. A very simple picture of thinking about is I kind of delay my phase transition up to a very high scale. That's there, for example, if I want to build a model for baryogenesis, it's still going to be electroweak baryogenesis because it's associated with electroweak symmetry, but not as electric scale. For example, one benefit is like EDM constraint, right? The one of the three sort of conditions is like CPU violation, and people are having difficulty building model for CPU violation because it is strongly constrained by EDM. But now supposedly I only need a cycle CPU violation at this very high scale. Now I scroll back down here, that's EDM constraint will be naturally surprised by this high scale here. Another interest that I think a lot of people here may be interested is talking about the stochastic wave background. So the peak frequency of your stochastic background from phase transition is pretty much, not exactly, but pretty much determined by your temperature and also a model. So typically, if you're at electric scale, your frequency is about a couple of hertz. Maybe some model can give you like 10 hertz each. But if you want to look at a stochastic wave background signature at a high frequency range, like 1000 of hertz, you need to have a phase transition that is at a very high scale. So there are more motivations. Today I want to talk about it too. But now talking about motivations. The idea of symmetry restoration is not new. Actually, I really like this very cute point model from Weber in 1974. So he wrote down this scalar potential with two sectors, and both sides protected by our own symmetry. But depends on your the couplings here in this simple Hamiltonian, that you can display a very different symmetry, breaking symmetry restoration along the thermal history. So these arrows tells you the temperature flow here, and depends on where you start from this phase diagram, you can have very rich possibility of symmetry breaking, symmetry restoration associated with this Owen plus Owen model. Of course, this is just to display the possibility of symmetry restoration more realistically. Symmetry restoration, non-restoration can be employed to discuss more rich topics beyond the one I just talked about. For example, there's exploration about spontaneous CPU validation associated with non-restoration behavior, and also can talk about multiple problems. Suppose the gut is not restored up to our high temperature, and also there's discussion in color breaking. So I put some reference here just to inspire you to explore more possibilities. So actually recently there's a development in discussing the electroweak non-restoration specifically, and the general idea is to couple the Standard Model Higgs with the scalar sector. You need many scalars, you'll see it soon. And here I'm showing you some different works. And the approach we're taking today is different from all these references here. So instead of realizing the symmetry non-restoration in the Standard Model Higgs sector, which is this red line here, we want to think about the possibility of symmetry non-restoration in a non-Standard Model Higgs sector. So explicitly here, we're discussing an inert Higgs model, but this can be applied to 2 Higgs doublet model, but general 2 Higgs doublet model, but we have a good reason to think about the inert Higgs. So basically, if you don't want to touch the Standard Model Higgs sector too much, you can enable a non-Standard Model Higgs sector that is also charged under electroweak gauge group, so through the GG prime. And then a non-zero vacuum expectation value of the inert Higgs can, of course, give you symmetry non-restoration up to very high scale here. So this is the content of our model. We have our standard model, and then we have a BSMS sector. Think of the dark sector where the inert Higgs is charged, and it actually group. It can talk to the Standard Model Higgs, but it's not really necessary. And then you need the scalar sector, of course, to induce symmetry non-restoration for the inert Higgs here. And today I'm going to be agnostic about what happens after the UV scale. So that is for future work. So you can have your UV sector here, where you can have a complete UV completion that gives you different behavior. And for example, if you restore the symmetry here at the UV, like through a first order translation, then you can talk about high scale baryogenesis or high frequency alternative wave as I motivated in the very beginning. So this is a summary of what I want to do here. And before moving on to specifics and show the result, I want to say one more theoretical consideration here. Actually, the reason behind this restoration, the main thing we want to achieve is baryogenesis. And in that case, the main consideration here is the sphaleron. Sphaleron is very dangerous for baryon symmetry because if it's turned on at any point in my thermal history, it is going to wash out my asymmetry that I worked so hard to create at a high scale very quickly. So we do want to keep my sphells inactive. And conventionally or like traditionally, you're familiar with this condition for strong first order phase transition. That tells you because the energy of the spell is proportional to the vacuum expectation value of your charged, the actual charged scalars. And then the spell rate will be exponentially suppressed by this energy. So that means if I roughly keep this criteria here, my spell is going to be suppressed as a function of temperature. To check this at any temperature along the Higgs thermal history. Of course, this is the kind of naive consideration. I'm going to tell you something more sophisticated. Hopefully, I have time. But we actually go beyond this criteria that I will make in the following. But very naively, if I think about this, that's going to tell me something about this blob that I cannot just skip over on the last step. So the blob is where our universe transits from the inert phase to our standard model phase, and we want to be at the standard model phase. And that can happen in different ways. I'm not going to explain these possibilities, but I just want to point you to the last thing here, where you can see the electroweak symmetry is actually temporary restore. This is something we don't want because at this temperature period, the spell is going to be turned on. So we do want to exclude this possibility. So we focus on the first two where you do have your spells always suppressed. So this is that's the theoretical consideration I want to say before I'm moving on to my model here. I have a lot of equations here, but this potential is a kind of most generic potential you can write down for inert to Higgs doublet model. So we do turn off two terms here, the blue terms, because of out of symmetry consideration. And then we also need to add a scalar sector. We call it chi's here. And you have a lot of freedom about the scalar sector. So for simplicity, we also turn off some terms. Those are totally irrelevant. So here is a handful of model parameters. A lot of them are actually not very sensitive to the symmetry restoration, but I do want to highlight this one. This one is a hero here. That's the particle coupling between the inert Higgs and the scalar. So it's like in the BSM sector. And this is going to give me an active contribution to the thermal mass. Keep in mind that I want my thermal mass to be active. And I will show you exactly how thermal mass depends on this. So I want this to be as inactive as possible, but it cannot be arbitrarily inactive because I have boundary from below from zero temperature considerations. The boundary from below tells me this parameter has a lower limit given by two other parameters. So this condition here plays an important role thinking about our parameter space. So now housekeeping. So I do want to say what do I do with my thermal potential? We imply the traditional one loop potential, but I'm going to have improvement on top of this actually related to the talk yesterday. But to start with, I have a one potential including zero temperature, finite temperature contribution. So this is rather non-analytic. So to gain analytical understanding of our parameter space as a model builder, I want to say if I have analytical handle there, and there is a very nice thing you can do with thermal potential is that you can do a high temperature expansion or small argument expansion of this Wissel function here. So with that, I land with this very nice finite temperature potential from one loop contribution where we recover your favorite thermal masses. We have thermal masses for all these three scalars here. But the one I want to focus is, of course, the thermal mass for the inert doublet. And you can see the last term is a term that plays a role here, which is a coupling between inert and scalar, has a multiplicity of number of scalars to have your model. And so now I highlighted this term, and we have analytical control, so I can look at my favorite parameter space. And we figure out that there are two parameters playing major roles here. On the y-axis is the coupling between the Standard Model Higgs and inert Higgs. Actually, this parameter plays more role for phenomenology consideration than the non-restoration, if I have time to go there. But the x-axis is the one that's crucial for non-restoration. That's the one I highlighted on the last slide. So consider non-restoration is going to remove this gray region. And imposing boundary from below condition, we impose all those conditions, just highlight the one that plays the most role here. I'm going to have different contours with different number of scalars. So basic scalars here help me to stabilize my potential with this party coupling. And of course, I talk about these two possibilities that happen at electroweak scale, and that separates my parameter space corresponding to different transition patterns. And then I want my strong rate to be surprised, so that further push me a little bit to the left. And lastly, I want to give you some guidance on phenomenology if you're concerned. I'm giving you some contours for different inert Higgs mass, and the phenomenology is going to put a cut here. And so this is like our very primary understanding of the parameter space, but it actually gives us very good guidance. And it also leads us to a very interesting regime where I can actually turn off my coupling between the Standard Model Higgs and inert Higgs. So in that case, the only coupling between my sector and the Standard Model sector is a H coupling there. So we do realize benchmarks where all these couplings are zero. So it's kind of just interesting, but for phenomenology, this is very important. So now this is just analytics with a leading order approximation. I don't trust it. I want to do my full one potential to numerically check what's going on here. Is my parameter space past the threshold of numerical check? But before that, there's one important caveat with one perturbative approach to my potential that is actually a topic covered by Oliver yesterday. So here we are taking a different approach, but here this is a very interesting topic, so I do want to spend a little bit of time on this. I feel this is very important for non-restoration phenomenology. There's a development in the community about non-restoration, but we really need to be careful with theories here because there is a caveat with one more perturbative approach. As you can see, I give you two axes here. X-axis is the temperature, so I can go anywhere from electric scale to very high energy scale, and the y-axis is a field value, so it can be any field, thermal field, or like inner field. And along the y-axis, we're going to have an RGE problem. So the one loop perturbative potential, or what we're familiar with common number potential, only gives you a log between your mass, depends on the field value, versus your renormalization scale. So if you fix your renormalization scale at somewhere here, you're going to have a large log here. So you need to go beyond the one loop, or say go beyond this leading log to resum more logs. Those are relevant. So formally that can be achieved by doing RGE, no surprise. But there's a much richer topic behind this. Actually, if you do one loop RGE, you're going to resum leading logs like this, like log to the nth order. So in fact, you're resumming higher loop diagrams. And a similar story is along the x-axis. It's just your control parameter is slightly different. So you can think about this control parameter as a ratio between your higher loop diagram versus lower loop one. So if you're like just around electric scale, it's fine. You don't have a large ratio here, especially suppressed by the coupling. But if you go to very high temperature, then this is going to be a large ratio. And you need to resum, again, higher loop diagrams. And formally, this can be dealt with this thermal resummation scheme. Like simply speaking, you just add a thermal contribution to your mass term. So you regularize your denominator here with a temperature. But the problem here is how do you determine what thermal mass have happened here? Formally, you can use this static equation. This is a differential equation. And you can think about this equation as kind of RGE equation at finite temperature, so finite temperature version. But this is like numerically disaster because you need to solve this differential equation at every point of your field space to determine where your local minima is. And also, it also depends on temperature. So a more effective way to do it is to use the approximation that I can truncate my contribution from thermal on the right-hand side. So instead of differential equation, I just do a derivative at every point of my field space. And the argument behind this is the thermal mass typically goes with temperature, so it has much less dependent on the field value compared to your typical like the zero temperature mass term here. And I just want to show something interesting. So if I do the high temp expansion on the right-hand side again, then I'm going to land at this very thermal mass term. So these are things are all correlated. Well, like in summary, so we do approaches, we take care of our control parameters on both axes in our numerical study. That's why we do benchmark studies. It's very expensive. So we pick up 2 benchmarks predicted by our analytical analysis, and don't have time, just want to show you how the inert Higgs behaves in real numerical simulation. And we also look at this ratio. On top of that, because my strong energy depends on the temperature and also depends on the field value, so it's kind of complicated. The best thing we can do is to do a temperature integration here to determine what is the dilution factor. So basically, we want to keep this dilution factor, the balance nature very small. But anyways, we do all these sanity checks, and we do convince ourselves that we can find safe benchmarks in our predicted boundary space region. And my last slide is going to be on phenomenology. I'm going to skip over. Perhaps the most relevant one you want to keep in mind is there's a lower bound on the inert Higgs mass, about 45 GeV from the stable sound invisible decay. So I do want my inert Higgs to be highly-ish. And otherwise, I can just turn all my cartolings and then I'm safe from phenomenology. And here comes to my conclusion and outlook. I hope I have convinced you that symmetry non-restoration, more specifically electric symmetry non-restoration, is a very funny playground to host the many new physics and the DSM phenomenology. And here in this work, we kind of give you a bridge here, a very solid stone bridge to connect your electroweak physics to a UV physics here. And for future work, we're thinking about doing some UV coefficient here, or UV model study that we can have a sense of what the UV baryogenesis looks like. And also we want to study the direction of this signal, just like use some point model and understand the signature of or like signature scale associated with this interface here. And I had spent some time on theoretical slide. This is a very intriguing topic. You can already say our approach is not a perfect approach. It works, but it's not a perfect approach, and it's very time consuming. So I hope there can be development in the community to have better theoretical control for high scale thermal field theory. All right, so